You probably know I like to solve physics problems, so I browsed through the online physics stuff and I found this problem, and I actually haven't fully looked at it, but it looked interesting enough. There's a lot of problems that I find that are just like, I don't know, not fun. But this looks like it could be fun, so let's look at it. And yes, I enjoy solving problems. Okay, I said that twice. A block is pushed against a spring with a spring constant of 12 kilonewtons per meter, located on the left-hand side of the track. I got a picture right here. And compresses the spring a distance 5.4 centimeters from its equilibrium position, right there. The block starts at rest and is accelerated by a compressed spring, slides across a frictionless track. It leaves the horizontal track, flies through the air, and subsequently strikes the ground. The acceleration of gravity is 9.81 meter per second squared. What is the speed of the v of the block when it leaves the track? I guess right here. What is the horizontal distance the block travels in the air, x? And what is the total speed of the block when it hits the ground? Okay, so it's kind of like a summary problem, I would say. Let me just redraw the picture, because I think it's always helpful when you're doing problems like this, just to go ahead and draw the picture. I mean, you would think, oh, well, there's already a picture there. But it does matter, okay? So I'm going to actually draw a couple of things. Here's the spring, and there's my block. There's my block. And there's my block. Okay, so I actually have three positions. I'll call this 1, 2, 3. And then let's write down everything we know. I know K is, I don't really want to do this, but 12 kilonewtons. 12 kilonewtons per meter. I'm going to call this compressed distance S. S equals, what was it? 5.4 centimeters, 0.054 meters. I convert that to meters, right? Because this is in kilonewtons per meter, which is newtons per meter. I can easily do that. So I'm going to need that in meters. The mass of the block, I need that. Oh, they have it over here. M equals 0.542 kilograms. This is going to be Y0. Y0 is 2.3 meters. Wow, that's pretty high. Yeah, I think I got everything. K. Yeah. Okay, so the first thing is, what's the speed of the velocity when it right when it leaves the track? So we'll call this V2. So in this situation, you could, what do we want to do? We could say, okay, I'm going to use Newton's second law, F net equals ma, and I don't want to do that, because what forces are acting on the block during this time it's being pushed? Well, there's gravity, there's a normal force, there's no friction, but there's a spring force. But the spring force is not constant. So that'd make work energy really difficult. I mean, you saw where I'm going. That'd make this really difficult. So instead, I could use the work energy principle. So that says work is the change in energy. And the key here is work energy because, 1, we're dealing with the spring. 2, we don't care about time, right? I only care about the change in position. And 3, I don't care about direction. So that's why I'm going to use the work energy principle. So this work energy principle says that the work is the change in energy. And we can't really do either work or change in energy until we do something very important, and that's to define our system. A lot of times we try to just skip over that, but if you skip over defining your system, what's going to happen is that you're going to have something on both sides of the equation. You're going to do work done by gravity and a gravitational potential, and so you don't want to do that. So I'm going to have the system of the block plus the spring plus the earth. And so that means that as this thing is moving, I have some forces acting on it. I have the downward gravitational force, mg. I have the upward normal force, and I have the spring force. The gravitational and the spring force are not going to do work because they're part of the system. The normal force does do work, but and I'm talking just about just going from here to there. But the work done by the normal force is 0. We define work for a constant force as F dot delta R. So in this case, the normal force is up, delta R is that way, so that these two are perpendicular, so the work done by the normal force in dot delta R is 0. They're perpendicular. So that's great, because now we have no work done on the system. But since I have the block, I have kinetic energy. Since I have the spring, I can have elastic or spring potential energy. And since I have the earth, I have gravitational potential energy. So let's go from 1 to 2 and write down the work energy equation. 0 work, change in kinetic, plus change in spring potential, plus change in gravitational potential. So we define kinetic energy as 1/2 mv squared. We define spring potential as 1/2 ks squared, where k is a spring constant, s is the amount it's compressed or stretched, and then ug is mgy, where that's the mass, the gravitational field, and the vertical position. So in this case, let's just write this out. 0 k2 minus k1 plus us2, that's a 2, minus us1 plus ug2 minus ug1. It's a change in potential. Change in energy. They're changes. So some of these are 0 and some cancel. So the first one that's 0 is k1. If it starts from rest, it has an initial velocity of 0, so this term is 0. Also, once the mass gets over here, the spring is no longer compressed or stretched. So us2 is 0. Finally, ug2, ug1 are the same, right? Because they have the same y value. They both have y0. So they cancel. So that makes it pretty easy. I get 0 equals k2, 1/2 m v2 squared. That's what we're trying to solve for, that v2, minus 1/2 k s squared. I'm just going to call that s. That's the amount it's compressed. Now I want to solve this for v2. I get, I can do it one step, but let's not. I get, move this to the other side, I get 1/2 m v2 squared equals 1/2 k s squared. The 1/2s cancel. Divide by m and take the square root. v2 equals the square root of k over m times s. So let's put in our values. It's going to be the square root of 12 kilonewtons per meter. So 12 times 10 to the third divided by the mass, 0.542, multiplied by s, 0.054. Put it in my calculator. Okay, so I have, I'm going to do this first. 0.054 times the square root, is that right? 12, 1, 2, 3, divided by 0.542, close parentheses, equals, oops, 8.03 meters per second. Okay, so that's the first part. Okay, next part. What is the horizontal distance x a block travels in the air? Answer in units of m. So this is not a work energy problem, because if I do work energy going from 2 to 3, there will be a change in gravitational potential energy. There will be a change in kinetic energy, but none of those depend on x. They don't depend on x, so I can't solve for x. So instead, we are going to have to use the Newton's second law. So let's just take the problem. Here we go. So here's y0. I know the velocity. I'm going to call that v2. And I want to call that x. It starts at x equals 0. So this is my origin right here. Once the block leaves the table, the only force acting on it is the downward gravitational force. That means that the acceleration in the x direction is 0 meters per second squared, because there's no forces in the x direction. The acceleration in the y direction is negative g meters per second squared, because that's the only force is mg divided by the mass, you get negative g. So this is your classic projectile motion problem. So in the x direction, I get the following kinematic equation. X final, which I'll call x3 because it's at the third position, equals the initial x position, x2, which is 0, plus vx times time. And so vx in this case, the initial x velocity, is v2. And there's no other term here because acceleration is 0. So this is going to be equal to x2 is 0, so I get v2 t. So that's it. If I know v2. If I know t, I can solve for x3. Pretty easy. This is the x motion. I always like to break. Now I can do the same thing for the y motion. In the y motion, I can write down the following kinematic equation. y3 equals y2. With I'm talking about the position that started at point 2. Trying to use my same notation I had before. Plus vy2 t minus 1/2 gt squared. So this is your basic kinematic equation. This is the initial position at the beginning of that time at t equals 0. This is the initial velocity at that time, and that's the time. And so in this case, at position 2, the y velocity is 0 because it's just moving horizontal. So this is 0, and that's going to be, I'm going to put it as y0 since I called it that before. Also, y3 down here is going to be 0 because it ends on the ground. So I get 0 equals y0 minus 1/2 gt squared. I can add this to both sides. I get 1/2 gt squared equals y0. And then I can multiply by 2 and divide by g. I get t squared equals 2y0 over g. Take the square root, and I get t equals the square root of 2y0 over g. And so that's going to be equal to the square root of 2 times, what was that height? 2.3 meters divided by 9.81. So let's get that time. You don't even actually have to get the time because you could just plug it in here, but everyone likes the time. So I'm going to say clear square root 2 times 2.3 divided by 9.81 close parentheses equals. And I get 0.685 seconds. Now I can plug that in up here, and I know the velocity. What was it? 8.03? Yep. So it's going to be 8.03 times the time of 0.685, and I get the final position of clear 8.03 times 0.685 equals. I get 5.5 meters. Okay, now we got one more part. What is the total speed, I'm going to say the magnitude of the velocity, when it hits the ground? Of course, this is one of those things that's kind of, when it hits the ground, I would say right, I'm sure this is what they mean, right before. When it hits the ground is such a difficult thing to even answer that you couldn't do that. Okay, so they want to say this. So it starts off up here going that way. At position 3, it's going to be going down v3 as a vector. So they want to find the magnitude of v3. Now, there's actually a couple ways to do this. And I wrote that time down so that I could do it this other way. So let's draw a picture. I'm going to do this part twice because I want to. So here we have, I'm going to write this as a vector v2. I'm going to write this as a vector v3. So I know t, I'm going to go ahead and write that down. I already solved it, and I could solve it again if I wanted to, but of 0.6, what did I say, 83? 85. And I know right here, v3, I know it has components. I know it has an x component and a y component. So I know v3x is equal to 8.03 meters per second. How do I know that? Well, that was the x velocity up here. There's no forces on it in the x direction, so the velocity doesn't change. So that's the velocity in the x direction. But I need to find the velocity in the y direction. So v3y equals what? Well, now I can use the kinematic equation. v3y equals the initial velocity, v2y, minus gt. Right? This is just from the definition of constant acceleration in the y direction of negative g. If I know the y velocity at point 2, which I do, it's 0. If I know g, which I do, if I know t, which I do, I can find this. So v3y is going to be negative 9.81 times 0.685, and I get, clear, I'm going to leave off the 9. 9.81 times 0.86, I said 6, 685 equals. I did do that right. I can't see that. Okay, I get 6.72 meters per second. Now if I look right here, let's draw this again. Here's my v3x, here's v3y, and I want this v3 magnitude. Well, that's a right triangle since the x and the y velocities are perpendicular. So v3 is going to be equal to the square root of v3x squared plus v3y squared. Just find the magnitude of that vector. So let's do that. So I have this squared plus that square rooted. So I'm going to say square root. Can you see that? There. This squared, 8.03 squared plus 6.72 squared, close parentheses. And I get 10.5. And that's the velocity at the end. Okay, let's do it one more way. Because let's go back up here. And remember I said I'm going to use my system including the Earth. I can actually do this in terms of the work energy principles. This is position 2 and 3. So I can say work is the change in energy. Again, going from here to there, there's nothing that does work on the system. Because there's no normal force. There's no air resistance, I guess. So I have 0 work, and that's going to be the change in kinetic plus the change in gravitational potential. There's no change in spring potential going from here to there because there's no spring. Okay. And so I can say 0 equals K3 minus K2 plus UG3 minus UG2. Now, I know this one. I know the velocity up here. I'm trying to find the velocity at point 3. I know if this is y equals 0 down here, then mgy3 is going to be 0. So I can just solve for my final velocity. So let's do that. 0 equals 1/2 mv3 squared minus 1/2 mv2 squared minus mgy0, right? Remember this is y0. So let's add these terms to both sides. I get 1/2 m v3 squared equals 1/2 m v2 squared minus mgy0. I'm going to multiply both sides by 2 and divide by m. I get v3 squared equals v2 squared. Oh, that's plus. Plus 2g, the masses cancel, y0. Yeah. You'll notice this is actually one of the kinematic equations. Okay. Final velocity squared, initial velocity squared, 2 acceleration times the change in position. Okay, just so you know. Okay. So let's just plug in my values. I get v3 is going to be the square root of v2 squared, which is 8.03 squared, plus 2 times 9.81 times 2.3. Is that how tall it was? 2.3. So let's put that in the calculator. Clear square root 8.03 squared plus 2 times 9.81 times 2.3 close parenthesis equals, oh look, 10.5. 10.5 meters per second. Get the same thing. Okay, wait. There's actually one more way. I know I lied. Let's go back to here, position 1. I could use the same work energy principle going from 1 to 3. I could skip 2. Who cares about 2? If you're just trying to find the velocity at the end, you could skip that. So if you do that, I'd say work equals 0. Again, the only thing force acting on the system is the normal force, but it has no work because it's perpendicular. Change in kinetic plus change in gravitational potential plus change in spring potential. That's the delta. So if I put everything in, I get 0 equals K3 minus K1 plus UG3 minus UG1 plus US3 minus US1. So some of these are 0. It starts from rest, so that's 0. The final potential is 0, so that's 0. The final spring potential energy is 0, so that's 0. So I get 0 equals 1/2 mv3 squared minus 1/2 ks squared. That's the initial potential energy in the spring. And then I have minus mgy0. So I should have done this on another piece of paper. That's fine. We can adapt. So if I do that, if I want to solve this for V3, I'm going to add these to both sides. I get 1/2 mv3 squared equals 1/2 ks squared plus mgy0. Now I'm going to multiply both sides by 2 and divide by m. I get V3 squared equals k over m s squared plus 2gy0. So if I plug it in, I get V3 equals the square root of k, 12 times 10 to the third, over the mass, what was the mass? 542. 0.542 times this compression, which was, goodness, 5.4 centimeters, 0.054 squared, plus 2 times 9.81 times 2.3. Okay, so this one, be careful entering into your calculator because you got a bunch of stuff. So let's do this. Clear. You got to say clear. Okay, so I'm going to say square root. Now I'm going to do this, 12. I'm going to do 1, 2, 1, 2, 3. And now I'm going to multiply by this. So times 0.054 squared. And then I'm going to divide by this. That way I don't use parentheses. 0.542. And then I can add this plus 2 times 9.81 times 2.3, close parenthesis, equals 10.5. Okay, there you go. That was an okay, fun problem. I had fun. It involved definitely, it's a weird problem because it's not a work energy or projectile motion problem. It's a work projectile problem. You can't do it just one way, right? There's no way that you can find the distance just using the work energy principle. Really, at the algebra level, you couldn't do this without work energy either, because you'd have to integrate over a non-constant force, which would be kind of difficult. Okay, hope that helps.